So we've already discussed a lot of these different encryption algorithms, all these different encryption standards, rather. So now we have to talk about keys. So one of the problems with encryption is this idea of trust. I mean, encryption makes it easy for us to exchange keys so that we can securely communicate with people, but how do we know we can trust that we have the right key and that the key has not been adulterated at some point in transit? So, in other words, if I have a message that I want to send to you and I ask you for your public key, um, so let's say you send me that public key, but how do I know that somebody didn't intercept that key in transit and give me their public key so that they could unencrypt the message and then encrypt it again for somebody else, right? And that's kind of what this slide is talking about. That's the classic man-in-the-middle attack. And there has to be some infrastructure in place where we can make sure that we have a way to trust those keys automatically to ensure the validity of those keys. And this is really important because modern encryption, if you think about it, I mean, we all know that most users are not, most normal users are not going to concern themselves with encryption if it's going to produce any work for them to have to do it, right? So we don't want to rely on people to have to do encryption. We want the technology to do it for them. And the technology needs some way to verify and to have some kind of mechanism for trust that's automatic and that's sort of foolproof. And that's what these public key infrastructures do for us that we're going to talk about here. And basically a PKI or public key infrastructure is sort of like the DMV. The idea is that we go to the DMV and we prove to the DMV we are who we say we are. I don't know the last time you tried to renew a driver's license or a state ID, but in the old days when I was a kid, you could go to the DMV and say, my name is Brian Green, and they would give me a driver's license. I didn't really need to prove who I was other than maybe give them a copy of my birth certificate or something like that. But good grief, if you've seen a birth certificate, they're pretty easily faked. So the DMV today, though, is much more stringent, right? So you go to the DMV today and you really have to prove you are who you say you are. You have to provide documentation. You have to provide multiple points of identification. You have to prove that, you have to bring them maybe a copy of some bills for your physical address. You have to show them your passport and so forth and so on. So the idea is that the DMV is pretty sure that you are who you say you are. And once you obtain that driver's license from the DMV, I can present that to anyone, and they can be reasonably assured if they can validate that that's a real driver's license, then they can trust the DMV because the DMV has already vetted you and has gone through the work to vet your identity. And that's really how PKI works. So we trust the third party, and we trust that that third party has done the due diligence, and that third party is ensuring for us that we are getting the correct key and helps prevent those man-in-the-middle attacks that I talked about. So basically, take some simple communication. Basically what happens is you have a user, in this case Diane, who wants to send a message. So Diane gets a certificate from John. So John presents a certificate, sort of like I would present my driver's license to a police officer to identify myself. So Diane gets that certificate, and within that certificate, embedded in that certificate, is the public key that Diane extracts from that certificate to encrypt the message. So if Diane can validate that that certificate is correct, that is a valid certificate, then Diane can be reasonably assured that the public key that is embedded in that certificate is in fact John's real public key, and that she's not the victim of a man-in-the-middle attack. To do this, so basically the DMV of the internet, of internet technology, I should say, is going to be certificate authorities, or CA. So a CA is a trusted authority that certifies identities and creates these digital certificates that I'm talking about. They establish an association between the subject's identity and their public key, the private key that is paired with the public key in the certificate and is stored separately. So the private key is that's paired with the public key in the certificate. It's stored separately from the certificate, I should say. So basically, we create that certificate. A CA basically is a central repository where you can obtain these certificates for users and verify their public key. A registration authority is a PKI component that accepts a request for a digital certificate and performs the steps of registering and authenticating the person requesting the certificate. So basically, an RA, a registration authority, is basically the moving parts that allow someone to request a certificate. There are 3 certificate classes, 1, 2, and 3. So class 1 is used to verify an individual's identity through email. Class 2 is for software signing, and Class 3 is for a company to set up its own certificate authority. So if you wanted to get a digital certificate, so let's say you need to be able to present a certificate when you're doing encryption, so you need to obtain a digital certificate. The first step is you're going to go to a registration authority, and you're going to register for a digital certificate. Then you're going to basically create a public and private key pair. In this diagram, step number 2 is basically you creating some random values to generate that public and private key pair. If you use some software, and I think in the lab I have you use some software to generate keys, and you'll see that some of the software will actually ask you to just bang random letters on the keyboard to try to generate random values. And that's how you generate the public and private key pair. So then the key pair is stored in the key store on your workstation. So you store your private and public key in the key store. Usually you password encrypt that, so you have a symmetric key that you use to encrypt that key pair, that file, so it can't be compromised. Then you're going to take the public key that you generated and you send that off to the certificate authority. The certificate authority then produces your digital certificate from that key, and they're going to use their key to do that. And then they're going to send the digital certificate back to you. And then you can then present that digital certificate to anyone with whom you want to encrypt data. And that's basically how digital certificates work. One thing that's important to note here is that even if you are, almost all of the asymmetric algorithms that use public key encryption, they all use digital certificates for the most part. And there really is no way to implement most of the algorithms, most of the standards that I've talked about. So the standards that I talked about, there really is no way to implement those without certificates, regardless of which one you're using. So even if you don't want to use a certificate, you still have to generate a certificate. It's just that typically you would just sign it yourself. So if you're using something like OpenSSL or something like that, you can generate your own certificates if you need to, if you're not going to use a certificate authority to do that. So essentially you become your own certificate authority. So it's not like you can look at this and say, well, I'm not really going to learn about digital certificates because I don't need to use them because I'm just going to, exchange a public key. But it doesn't work that way. You have to use certificates. All of the algorithms sort of assume that you're going to be using certificates. So, so you'll have to just sign your own certificate and configure your software to accept those self-signed certificates on both sides of your secure communication. So, and that's kind of leading me into this idea of a local registration authority. So a local registration authority performs the same functions as a registration authority, but you implement it internally. So instead of communicating with an RA, each site can have its own LRA, and it reduces the traffic created by lots of users trying to make requests across a wide area network. So you can have a local registration authority. A certificate repository is a centralized directory of public keys and certificates that can be accessed, basically so you can go and obtain a digital certificate. For example, if you're on the web and you want to go to Amazon.com, obviously you want Amazon.com to be encrypted if you're going to send them your credit card number. So your web browser goes to a certificate repository, could go to a certificate repository to get that digital certificate. In reality, what really happens is your web browser gets a digital certificate from Amazon, and it goes out and validates that certificate against a root CA, which we'll talk about later. But most of these certificate repositories are LDAP compliant, meaning that that they work with LDAP. We've talked about LDAP in this class before. One of the reasons I really wanted to get you guys exposed to seeing LDAP and working with LDAP is once again, it's used for certificate repository. So I think you may have seen in LDAP, there's this whole substructure in LDAP for querying for information, for network information against LDAP. We looked at that prior. We looked at that for user accounts, but LDAP could also be used to query for certificates. So basically, you want to verify a certificate. So if somebody presents a certificate to you, you may want to verify that it is a valid certificate. And the way you do that is by going to a root CA. Basically, a trusted CA. It basically are the certificate authorities that you trust. So these are people who have issued certificates that you implicitly trust. Therefore, you trust the certificate that you've obtained. And you can validate certificates against those CAs. So you can go to a CA and say, is this really a valid certificate that I've obtained from user A or whoever it is? In fact, if you look in your web browser, so if you're using Internet Explorer or Edge, you can get to a screen that looks like this, where you can see a list of all of the default certificate authorities that are trusted by the web browser when using SSL or TLS. And you can add additional ones if you want. So you could add your own root certificate authority. Maybe if you're using self-signed certificates, you could add those. If you're using them internally, you could add those. You could do something like that with group policy or something as well. Although it won't have any effect on Chrome or Firefox. So in any event, you can go into Windows and you can see who your CAs are that you trust. So to verify a certificate, so let's say somebody provides a certificate to you and you want to verify that that certificate can be trusted. So I already talked about how to obtain that certificate. So now if you got someone's certificate, somebody sent you a certificate and you want to extract their public key from that certificate because you're going to exchange data, so you have to extract the public key, but you also want to verify that the public key, that overall certificate and thus the public key are trusted, that they really came from that person. You would take that certificate and you would extract the message from the digital certificate, and you would take the digital certificate and you would do a hash algorithm on the certificate, and that gives you the message digest, which in this case is message digest A. Then the CA, the certificate authority, also produces a message digest on their side, and you compare their digest to your digest, and if they match, then you know that you have a good certificate, and you can read the message. If they don't match, then you assume that there's been a problem, there's a mismatch, and you don't read the message. If you're using a web browser, this might manifest itself as a warning that comes up and says, get me out of here, you can't trust this website, it doesn't match, the certificate doesn't match, or whatever. And a lot of us just hit the button to go forward anyway because we don't care. But that's a big red flag that most people tend to ignore. So that's basically how verifying a certificate works. All right, so digital certificates. So a digital certificate binds an individual's identity to a public key, right? That's the whole purpose of this, is that, if I have a public key, I can bind that public key to my identity, which can be vetted by a third party. So some of the fields that you might see in a digital certificate, you can look at them again in Windows. I think in the lab I have you do this. I have you go through and take a look at some of the fields that you would use in a digital certificate. There's a lot of stuff in there. Things like what algorithm you're using for the signature, what hashing algorithm. So you can see in this case they're using SHA-1 as the signature for the hashing algorithm. And we already talked about hashing algorithms. So already we're starting to see some of these standards in the real world. And you can certainly go into Windows and you could look, not in Windows, but in Internet Explorer in this case, and you could look at the details in something like IIS if you're going to request a digital certificate. All right, so some of the attributes with certificates. You have an end entity certificates are issued by a CA to a specific subject. The CA certificate can be self-signed, or it can be issued by a superior CA within a hierarchy. So here's an example of a hierarchy, right? So if I am a user, on one side of this hierarchy, and I see that it's been signed by the CA at the lower side of the hierarchy, I can implicitly trust the other side going through the root CA. So there's sort of that transient trust going through the root CA. So most certificates have a life cycle, and you have to determine the proper length of the life cycle, because a shorter lifetime is good because it's going to limit the ability of an attacker to crack the certificate. or to break that certificate. But a longer lifetime produces lower system overhead. In other words, lower or longer lifetimes are better for performance and efficiency, but shorter lifetimes are better for security. So once again, we always have that sort of, we're trying to weigh performance and availability against our level of security. So that's certainly something you have to consider. So we can't just make super short lifetimes because it's, very, very secure. There's also some performance things we have to think about as well. So we have to kind of find a happy medium. Once a certificate exceeds its lifetime, or before it exceeds its lifetime, you can do a renewal. So if a certificate is close to when it's going to end, you can request a renewal, and then the certificate's renewed, and then you can continue operating. If for some reason the certificate is expired, then you have to request a new certificate if it's expired, which does require a little bit more computational power. Certificates can also be revoked. So a certificate can be revoked if its validity needs to be ended before its actual expiration date. So this could happen if the private key has been compromised. So somebody wants to make sure that no one attempts to use their public key, because that data could be unencrypted by somebody else. So they want to make sure that no one's using that key anymore. I have a new set of keys. So I could revoke that old certificate so that it's not used. So that's certainly the main reason that we would revoke a certificate. If you check with a CA and you see that a certificate has been revoked, it'll usually give you a reason code, and these are the reason codes, although they typically will show you in the, like if you're using a web browser or something like that, you would see the reason right in the browser. It'll tell you why it's been revoked, or it'll say it's been revoked for the following reason or something like that. So I'm scrolling through a few slides here that you can go back through in YouTube or in the video if you're watching this in another version of the video playback. But this basically is talking about the certificate revocation list, which has to be shared. So one of the challenges with revocation is you have to somehow notify everyone that a certificate's been revoked, and that can be a bit of a challenge because that list can get rather long. If as you revoke more and more certificates. Obviously, once a certificate is expired, you no longer have to have it on the CRL. But if you have a lot of revocations prior to being expired, then that list can grow rather lengthy. You can also suspend certificates. Suspension of a certificate is usually to hold that certificate for a period of time. Maybe something, for some reason it's not going to be used for a while, so you could suspend it for some period of time, and then when you're ready to use it again, it's no longer suspended. So kind of like in the old days, we used to all get newspapers. When you go on vacation, you suspend the service for a while, and then you come back and you start getting your newspapers again. Kind of a similar idea. So private key protection. The key size should provide the necessary level of protection for the environment. And then you have the lifetimes. So lifetimes are important. I talked about lifetimes before, but basically a lifetime is how long you're going to use those keys. So the lower the lifetime, the higher the security, but the more overhead there's going to be. So it's important to be aware of how lifetimes affect performance, but they're also better for security, these shorter lifetimes. Obviously, you don't want to share your private key. If you share your private key, then it's no longer useful to you because now anyone could read that information. Authentication should be required before a key can be used. The key should be transported securely, etc., etc. So just a lot of common sense things about how we deal with private keys. Usually when you store a private key, you store it in a password protected file. That way it's much more difficult for it to get compromised. So there are public certificate authorities that are already established and being used by lots of other individuals and companies and things like that. I'm sure you've heard of a lot of these public CAs like VeriSign, GeoTrust, Entrust, GoDaddy, and so forth. I think one of those in that list may not be actually used anymore, but in any event, there's a whole list of these public certificate authorities that are being used. But you can also be your own certificate authority in-house. So in your own infrastructure, in your own IT infrastructure, you can be your own certificate authority. A good example of this is if you have Active Directory in your corporate environment. In many cases, with Active Directory, Active Directory can act as your certificate authority as well, so that it's mediating the trust on your network. And since we set up that Active Directory server, we trust it. It's so forth and so on. So we could just use that internally, and it'll save us from having to use a public CA or having all that traffic over the internet, for that public key infrastructure. But again, if you're using the internet or using anything that's on the public internet that's outside the scope of your organization, then you have to use a public CA for that sort of thing, for a variety of reasons. There's really no way to cache all that stuff unless you're you're one of those public CAs. So a trust model. So there are various forms of trust. You have hierarchical trust, peer-to-peer, and hybrid. And basically, a hierarchical trust model is when you generally have a root. So with hierarchical trust, you've got a root, and below that root, you have branches. And if anybody in that branch gives you basically your trust can go through the root, right? So you can go up through those branches and then back down through another branch, and there's a transient relationship there through which you can trust. But peer-to-peer is where you can trust anyone in sort of a mesh of nodes. And then you can have a hybrid, which is sort of a combination of these different trust models. So a hierarchical trust model is a basic hierarchical structure. You have a root CA, then intermediate CAs, leafs, and then end entities. So the root CA is the ultimate trust anchor for all the other entities in the infrastructure. So it generates the certificates for all the intermediate CAs, which in turn generate certificates for the leaf CAs, and the leaf CAs generate certificates for the end entities, the users, network devices, and applications. So no bidirectional trust exists. It's all from the top down. In other words, it all comes from that root CA, and it permeates down through the entire hierarchical structure. So there's no peer-to-peer. There's no lines that go back and forth left to right. They all go from the top to the bottom. And this slide just demonstrates the certificate path of how how you would basically vet the validity of a certificate, but also sort of how the at what level you're doing what level you're getting trust. So you can see here at the bottom is where your users and devices and so forth are that actually obtain those certificates, and then leaf CAs get their certificates from the intermediate CAs, which get their certificates from the root CA. In a peer-to-peer model, there is no one CA that is subordinate to another CA. So you have sort of these different CAs that trust each other. What's important to note here is why would we need to have CAs that trust each other? If you think about it, how could there be just on the public internet, for example, it wouldn't be wise to have one company that is the root CA that operates the root CA and to which everyone else is subservient to. Let's say VeriSign, which is a pretty well-known company as far as trust goes on the internet. If they were the only root CA, then what happens if you don't want to do business with CA, or if CA goes out of business, or whatever? So there has to be different companies that can be a root CA, and those different companies are a peer-to-peer model. In other words, VeriSign trusts Entrust, which also trusts GoDaddy, and so forth and so on. So they all trust each other, but then there could be a hierarchical structure below those, and that's what a hybrid trust model is. So the hybrid trust model is where we have sort of these trust anchors at the top that trust each other, and they have very well established way of trusting each other, but then below they have a hierarchical structure below them. So you can see in this example we have a bridge CA between these various root CAs, which all trust each other, and then below the root CAs is that hierarchical structure that we talked about before. You couldn't really have the entire internet on a peer-to-peer trust because it would be just way too complicated. So there has to be just a finite number of root CAs that we trust, to which there is a hierarchical structure below, where those updates and revocation lists and all of that are carefully controlled. And finally, certificate-based trust. Certificates bring a lot of capability to security. through practical management of trust, but they can also present several threats. And I guess the biggest threats are to me, one of the biggest threats of certificates is complacency. We get this, it works so well for us to develop this trust in the system that we stop questioning that trust. And that's kind of the biggest risk here is when we stop questioning that trust. And this is what happens. If you think about it, um, when you go online and you go on the internet and you go to a web page and Chrome or Firefox or Internet Explorer might give you a warning page that says the page you're going to doesn't have a valid certificate. And a lot of people will see that warning message and just click the button and continue on to the website anyway. And then 10 minutes later, put their credit card number in and not even think twice about the fact that 10 minutes ago, the browser told them that website can't be trusted. And a lot of times those problems are benign, but we're kind of sensitizing the user just to assume that the encryption always works and that it's valid and that it's secure. And a lot of us do this to ourselves, as IT security managers. One of the big trends right now is using proxy servers like WebSense and things like that, where we want to monitor the traffic or the websites that people are using within our organization, and we have a right to do so in most cases to monitor the usage of the web within our organization. It's our internet and so forth. People don't generally have a high expectation of privacy when they're working at a company that has a clear acceptable use policy that talks about being able to monitor that traffic for a variety of reasons. A lot of times we have legitimate reasons to monitor web traffic. We're looking for data leakage and things like that. I work in healthcare, so a lot of times we're concerned about about HIPAA people sending patient data over the web or uploading things onto the web by mistake even. So we'll put these devices in like WebSense that will basically monitor all of their web traffic. But in order to do that, if you're using a website that has encryption, we have to basically do a man-in-the-middle attack to monitor that traffic. So what we'll do is WebSense will go out and do the encryption with Amazon.com, and then internally do that encryption again to the end user inside our network. But when that happens, because the certificate system works, because that trust works so well, the web browser realizes that there's somebody in the middle. The web browser says, wait a second, there's somebody in the middle that's intercepting this traffic. I know that. I'm going to warn the user. And because the users are so used to that, the users see it all day long. Every time they go to a HTTPS site, they see that warning message. They just click the button to go through. Well, that one time that trust actually has been compromised for real, the user is not going to know because they're so complacent, they're so sensitized to that warning. So that's a good example of how we're kind of getting burned sometimes with certificates because the system works, but when it is compromised, if you compromise that trust, that's the worst kind of compromise there is. Take for example in the real world, if somebody figures out a way to make a fake ID that is indistinguishable from a real ID, then the TSA is now going to have a major problem because how do they know which driver's licenses to trust? If somebody's been able to fake driver's licenses to and basically work around all of the security features that are baked into things like driver's licenses. So you can kind of imagine how important trust is and how big a deal it is when trust is broken. And I'm sure you've heard the stories and have seen things online about when there are issues with the certificate authorities and things like that. There's been stories in the past about how they've been hacked and somebody's been able to get the root certificates for some major certificate authority and has been able to hijack public keys and things like that. So it certainly does happen. It's certainly something that we have to be aware of. All right, so that's it for certificates.